Swayam Prabha. Digital India. Educated India.
Hello everybody. So, welcome back to my course, that is the reactive intermediates carbene and nitrene. Today we are here to clarify some of the doubts that you have posted in the forum as well as here in the post. I will try to clarify as much as possible. Even though we have discussed a lot of those things during the our course, but still some doubts are there among you. So, I will try to clarify those doubts. Okay. So, first doubt which I found in the forum, that one of the students he or she is asking about the structure, electronic configuration, structure and geometry of these carbenes, which we have discussed in initial classes. Anyway, if we again look into that in very broad way, that the carbenes, if you see, they are in general singlet and triplet. Okay. So, now among this singlet and triplet, this is totally depending upon their electronic structure. Now, the nature of the ground state, that depends on the relative energies of the two non-bonding orbitals. Okay. So, the main thing is the relative energies of the two non-bonding orbitals. Okay. Now, if we see that triplet state, so this is the p orbital and this is the sp2 orbital, and electrons are in parallel spin and in different orbitals. Okay. And definitely this is the sp2 hybridized center. Okay. So, this triplet carbene, this is bent carbene. I will come into more details about what is its bond angle and other things. However, for singlet carbenes, this p orbital that remains empty, rather these two electrons paired up in one orbital, that is into this sp2 orbital. Okay. So, the two electrons that occupy the lower of these two available orbitals with spin pairing. Okay. So, this is the corresponding, this is also bent carbene, and this is the corresponding singlet and this is the triplet. In this case also this is having this sp2 hybridized center, carbon center. Okay. So, these are all sp2 hybridized centers are having, but in case of linear carbene, there are two p orbitals which are diagonal to each other. Okay. And these orthogonal p orbitals are, in these two orthogonal p orbitals, the electrons are there in parallel spin. So, this is nothing but sp linear carbene. Okay. And these are having this p orbitals, where these two p orbitals, these 2 electrons are staying. Okay. So, these are the sp linear carbene. Now, you know that already from the course that most of the carbenes are not linear, rather they are bent in nature. If you see its geometry, if you see its geometry for this triplet and singlet carbene. So, for triplet carbene, you can think about, I am just drawing in a so, for this triplet carbene, so for this triplet carbene, if you see this bond angle, okay, bond angle is around 130 to 150 degree. So, as per VSEPR theory, the bond angle should be higher than the 109.5 degree, because if you see here only one electron is there, whereas in this case, in case of singlet, this bond angle is rather 100 to 110 degree due to having here 2 electrons. Okay. So, greater repulsion, and that is why this bond angle decreased and that becomes within 100 to 110 degree, whereas in this case there are single occupied, and that is why this repulsion that is less. So, that is why the bond angle is higher and it is 130 to 150 degree. So, these are the total geometry and the electronic configurations of these carbenes. And now, if you see their MO structure, as one of the student asked there, in the forum about their MO. So, we know that the triplet state is lower in energy than the singlet state. Okay. Triplet state is lower in energy, because the electron repulsion energy exists between these 2 electrons in a single orbital. If it is higher than the energy that is gaining by bringing the p orbital electron down into the sp2 orbital. So, in that case what you will get, in that case obviously the triplet state is lower in energy than the singlet state. Okay. So, this is the reason. So, in one case you have to think about that how much energy you are gaining by bringing down one electron from upper level of this higher energy level to the down one. If you can bring them, so it will be paired up, but in that case also, in case of singlet, there will be the repulsion between each of these 2 electrons. In that case, if that repulsive energy is higher than bringing down this electron from another higher orbital to the down one, then if it is higher, then obviously they will be like a triplet, but if it is lower, then it will be singlet. So, in that case how it can be rationalized, that if that energy gap between these sp2 and p is very high, okay, very higher, then in that case you will see that obviously it will be in a singlet. Okay. But if that energy gap is lower, in that case it will stay as a triplet state. Okay. So, that is the reason, because there is a repulsive energy between these 2 electrons when they are in a singlet state also. So, that balance is necessary, that is dictating, or that is actually guiding that whether it will be in a singlet state or it will be in a triplet state. Clear? Now, if we see its MO for this singlet one, okay. This is the bent singlet, and in that case Okay. But in case of triplet, they are in this way, this bent singlet and bent triplet, that is their electronic structure are there. Now, this depends on all about this difference. Okay. So, how much in case of this singlet carbene, if these two are here, then they will have some repulsion between them, but again if they will be in a triplet state, when you are bringing them down, then they are gaining some energy. So, you have to calculate both of them, and then only we can understand that how this triplet state in some cases it is getting stabilized, and in some cases the singlet state is stabilized. Okay. So, in that way we can understand that the singlet carbene and triplet carbene and their electronic structure. Okay. And in case of linear carbene, they will have these two degenerate p orbital. If you see, they have two p orbitals which are having similar in energy, and in that case these two electrons that is singly occupied there, and they will give you the corresponding linear triplet carbene. Okay. In another in forum questions, there is another doubt about the students, that why this CHCl, that carbene, or CCl2 carbene, or COMe2 whole 2 carbene are singlet carbene. Okay. So, that is one of the this carbene's nature, that why some of these are singlet, and whether in some cases like CH2 carbene or CpH2 carbenes, they are triplet carbenes. Okay. So, let us discuss why these CCl2 carbenes or CHCl, they are singlet carbene. Okay. So, carbenes are which are having these electron rich substituents or heteroatoms having lone pairs, those type of substituents that can donate electron. Okay. Electron pairs, they may stabilize the singlet state by delocalizing the pair into an empty orbital. Okay. Of course, in case of singlet carbene, you have seen there is one empty p orbital. Now, there all these substituents that can donate their extra electron pairs to stabilize this. Okay. So, in that case substituents that can donate electron pairs may stabilize the singlet state. Okay, by delocalizing the pair into an empty p orbital. Okay. So, let us see that how it can do that. Let us say have this, you have this carbene, now X is having this lone pair. So, it can actually donate here to the empty p orbital to stabilize this. Okay. Now, if the energy of the singlet state is sufficiently reduced, it will be the ground state. Okay. Now, after donating of these extra electron pairs into the vacant p orbital, now the singlet state is sufficiently reduced, the energy of this singlet state, and of course, then it will be ground state. Now, we will see how it can be how it can rationalize because of this adjacent lone pair that can be donated into the vacant p orbital, and in that case you have this sp2 and this is one p orbital. Okay. Let us say it is in this case, and now you have this field n orbital. Okay. So, in that case you see now this after donation of this electron pair from this heteroatom or these halogens over there. So, basically you are actually the energy of this singlet state is getting sufficiently reduced. Okay. So, if you see that is getting reduced here, okay. And in that case you can see that in that way this particular carbene, singlet carbene becomes stabilized. Okay. And that is why having this halogen into it and which can donate actually electron pair into the empty p orbital, then in that way it can this way this CHCl or CCl2 that are becoming singlet carbene, okay, because they are getting stabilized by this by reducing energy. Okay. So, in that way that is why these CCl2 and CHCl they are singlet carbene. Next, another very interesting questions is there in the query. That during the cycloaddition of this alkene corresponding alkene to by this singlet carbene, we mentioned that this is like a concerted manner it is happening. Now, some student asked that how this HOMO LUMO they are interacting, that he or she wants to know. Okay. We will see that 1 plus 2 cycloadditions by this singlet carbene with the corresponding alkene. If we see the MO of this alkene, okay. So, this is the double bond, and in that case if we draw its MO, this is the corresponding HOMO and this is the LUMO, because this one these 2 electrons this is having over here and this is the highest occupied molecular orbital and this one is the LUMO, lowest unoccupied molecular orbital. Fine. Now, the interactions will happen between the either with alkene HOMO with carbene LUMO for the reactions, because you are let us say you are reacting with this. Okay. So, the reaction is happening between this one and this one. So, you have to consider the MO of this olefin as well as the MO of this corresponding carbene. So, in that case if we see this alkene HOMO, then we draw that okay. Let us say we have drawn this alkene HOMO and that is the field pi, and in that case we will do the carbene LUMO. This is alkene HOMO and we will draw the carbene LUMO. So, carbene LUMO means for the singlet carbene it is the vacant p orbital. Let us say we are drawing like this. Okay. This is the empty p orbital. Now, if we want to interact with them, then you see that this one is giving the bonding interaction, no problem at all. But when you want to check this one, this is giving the anti bonding, which is not favorable. That means this is not happening. So, because both has to be bonding, then only this bonding formations can possible, but with this one orbital is giving this bonding, another one is giving this another lobe is giving the anti bonding one. So, that means this is not possible, okay, because orbital symmetry in direct approach, orbital symmetry for this is called direct approach. So, these orbital interactions during this direct approach, we have seen that orbital symmetry is not matching. So, that is why this is orbital symmetry in direct approach is not working. So, in that case we can think that definitely it is not happening in that way. So, what we can think about the opposite way, that let us consider alkene LUMO, not alkene HOMO, rather alkene LUMO. So, we will take now alkene LUMO and we will consider the carbene HOMO. Okay. So, we will draw that. This is the corresponding empty pi star, that means this one. Earlier I have seen that is the HOMO one, that is the field one, and field pi orbital, and in this case this is the empty pi star. And if we see this one is having like, okay. Now, if we take the carbene HOMO, you have seen that in case of carbene HOMO, HOMO is nothing but for the carbenes is field sp2 orbital, and in case of field sp2 orbital. So, this is the corresponding HOMO. Now, you see it is not, this is giving the anti bonding, though this is giving the bonding. Okay. That means, in this way also this is not possible. So, direct approach is not possible for both the cases, because either you take carbene HOMO or you take carbene LUMO, because this is having p orbital. So, it is coming in this fashion, and if you having this HOMO, carbene HOMO of this you are taking, in that case it will come in this fashion, and both the cases it is not giving the entire bonding interactions. So, direct approach is not possible for this type of concerted reactions with the singlet carbene and the olefin. So, what we have considered then, that direct approach is impossible. Fine. So, definitely, but the reaction is happening. So, what is the way that it is interacting then? Okay, this is making the bonding interactions. So, let us again see the corresponding olefins HOMO. This is the field pi like earlier. Okay. And this is the corresponding this is alkene HOMO and this is the carbene LUMO. So, in this case this is the empty p orbital, like earlier we have seen that empty p orbital is the LUMO for the carbene, and in that case you see that it is nicely giving the bonding interactions for both the cases. Okay. And this is called sideway approach of carbene towards alkene. So, direct approach is not possible, but sideway approach is possible. You see nicely giving bonding interactions. Let us see the opposite one, that means you take alkene LUMO and then take carbene HOMO. And okay. So, what is this carbene HOMO? We knew already it is the filled sp2 orbital. Okay. And what is this alkene LUMO? That is the empty pi star. Okay. So, now you see in this case also the bonding interactions possible very nicely. So, sideway approach is the best feasible for this type of reactions or this type of cycloadditions, where this concerted mechanism is following for this singlet carbene with this olefin. Okay. So, if we see in a very in a particular example like this, like this, now these hydrogen atoms that swings round into place to give the corresponding cyclopropane derivative. Okay. So, in this case you see there you have taken cis conform this cis geometry over here, and you are getting this both particular stereochemistry for this cyclopropane. Okay. That is, if you take trans over here, then of course, here you will get the corresponding trans one. Okay. So, this is highly stereo specific in that sense. Now, another question was there in the forum, that what is this dimerization of carbene, that we will discuss, and then followed by why this dimerization is not happening for these n heterocyclic carbenes or these nitrogen contain nitrogen in nitrogen nitrogen heterocyclic carbenes or n heterocyclic carbenes, and of course, why this type of carbenes are stable, or why this type of carbenes are called persistent carbenes, that we will discuss. That is also another questions by another student. So, both we can discuss in one particular question. So, first we will see this dimerization of carbene. What is this dimerization of carbene? In many cases we have discussed about that in a lot of this type of dimerizations are possible in for several carbenes as a side reactions. So, the two carbenes or carbenoid precursor react in a formal dimerization to give an alkene. Okay. One important thing is that it is very much concentration dependent. So, if you take it in a very concentrated way of these carbenes, then of course, there will be some side reactions to give you this dimerization. Okay. This is often considered an unwanted sign reactions. So, we will see this. So, you have this. This is very fast at higher concentration. Then they will give the corresponding olefin dimerization, and this dimerize to give some olefin. Now, generally these carbenes, when it generated in the reaction medium, it needs immediately some target compound, because it is a short lived species, you know, and in that case it reacts very fast with the target compound. And that is why when these carbenes are generated, they are generated in situ, and their target molecules with whom it will react, that is also there. So, they react immediately, and one another important aspect for this particular type of avoiding this type of side reactions is that you have to keep the concentration of these carbenes very low. In that case, it can avoid the dimerization. Okay. If the concentration is high, then of course, there is a chance of becoming more dimer. Okay. Now, you have already I have discussed in during the classes that you have seen that this type of dimerization is prohibited for heterocyclic carbenes. Okay. Mostly when there is this R group that is bulky. What is this I am discussing about? That let us say you have this carbene, these heterocyclic carbenes. Okay. Now, these carbenes are stable, this is not going for dimerization. Okay. And additionally they are nucleophilic in nature. This is very particular characteristics for this type of N heterocyclic carbene. This is N heterocyclic carbenes. Now, during this N heterocyclic carbenes, that bulky substituents that attach to this N center, that prevents such dimerization due to the steric interactions. Now, somebody asked why this type of carbenes are stable. So, I will not only these particular reasons, there are actually few reasons or few characteristics are there for this type of heterocyclic carbenes, which make them stable or which make them persistent carbene. Okay. First is that we know all these carbenes are electron deficient, okay, but this electron deficiency that is reduced by the donations of this nitrogen lone pair. You see nitrogens are having lone pair over here, and that can be this electron deficiency that can be reduced by this donation of nitrogen lone pair. I have discussed this type of phenomena over there during our classes also, that this electron deficiency is reduced by donations of nitrogen lone pair. Okay. Next is that this carbene electron pair that is getting stabilized again by the inductive effect of these 2 electron negative nitrogen atoms. Okay. So, this carbene electron pair that is over here, that is getting. So, this carbene electron pair is getting stabilized by the inductive effect of two electronegative nitrogen atoms. Okay. So, that is basically like this way. And number 3 is that very important is that which I was discussing for this dimerization thing also, that in this for this type of n heterocyclic carbenes, this dimerization is prohibited because of this bulky R group. Okay. These bulky R groups prevent the dimerization. Okay. So, this is these are the reasons that why these n heterocyclic carbenes are stable and why they are called as persistent carbene. Clear? I hope that these all dimerizations and the relations with this corresponding their stability and other things has been clear. Next, another questions was there in the forum, rather I will discuss that one finally, that regarding this formations of the CCl2 carbene from the chloroform. Okay. So, CCl2 carbene we see it can be generated from the chloroform, okay, with the base, let us say sodium hydroxide. So, if we draw this, sorry, if we draw it with chlorine. Now, due to presence of these 3 chlorine atoms over here, this hydrogen becomes extremely acidic, and if you give the base, it will pick up this acidic proton and generate one carbon ion, which is a charged species. Okay. Now, once from this carbon ion, the chloride removal give you the neutral species, okay. And this neutral species generation is important, that is why this chloride is leaving over here, and the electrons form this carbon chlorine bond that leaves with this chloride ion, and that is why this is giving this neutral species. This is important because getting neutral species is important in particular reactions. So, from the charged species you are getting the neutral species, which is again sp2 hybridized, having sp2 hybridized carbon over here. Okay. So, this is another discussions that I want to do it here, that you are starting from chloroform, okay, and you are ending up into a, that means from one neutral species you are generating another neutral species. So, due in the presence of sodium hydroxide. So, that is why this reaction is feasible over here. Okay. And in another questions that some student asked about some chemoselective reactions, though it is not much related to this carbenes things, I still will like to address this, that what is this chemoselective reactions, and somebody is asking about regioselective reactions, all those things. Obviously, regioselective reactions means that is like a region specific. Let us say you have variable positions where the reaction or the where these reactions can occur, that particular center, but if the reactions happens even in the particular positions with respect to other position which are almost equivalent, in that case that will be called like a regioselective. Like let us say in a benzene, okay, you have ortho, you have meta, you have para position. Okay. So, now if selectively in one place something can be introduced, that is be called as a regioselective. Okay, fine, because you are actually introducing in a particular center and your required functional groups. So, in that case that is a regioselective. And in case of chemoselective, let us say you want to do when there are two different functional groups are there, and in a particular reactions you are only able to either convert or react with that particular functional groups, that is called chemoselective reactions. Okay. And finally, I would like to discuss one more thing from the forum questions, that is there any forum questions? No, as there is no more further forum questions. So, I will discuss one more rearrangement reactions, that is called Doering-La-Flame alene synthesis. Okay. That is also another queries from these different years, it is always coming regarding this particular alene synthesis, that so, now in case of alkene, these reactions of alkene that converts into the allenes by insertion of a carbon atom, okay, that is Doering-La-Flame alene synthesis. So, first let us say then you generate the carbene, okay, and now this carbene can rearrange to the corresponding alene. So, this is a two step reaction. Okay. And first is that reactions of this dihalocarbene with the alkene to give the cyclopropane derivative, and then the corresponding carbene generations, and after that this carbene that can rearrange to the corresponding alene. So, this is the Doering-La-Flame alene synthesis. Okay. Because often we give a lot of questions and assignments with such type of rearrangements. So, I thought to give it for this particular case, that where you can have all this type of rearrangement, especially in another case you can have these insertion reactions also for different type of rearrangements, like if you have this heteroatom that can insert into the corresponding electron deficient carbene center, and after that lot of rearrangements can happen. So, these are very important for such type of rearrangements where these carbenes are involved. Okay. So, I think with this most of the doubts that is there in your queries that I can address over here, and I think that will be this type of discussions will be helpful for you to go further with this course, and thank you very much.